Welcome everyone. I'm Jafar. So, welcome to this week two of problem solving in the course Control Engineering by Professor Ram Krishna Pasumalthi, Department of Electrical Engineering, IT Madras. And as you all know, I am a Prime Minister's Research Fellow at the Department of Electrical Engineering, Indian Institute of Technology, Patna. Okay. So in today's session, we'll be solving problems on Laplace transform, whatever actually you have learned in the last week. For example, you have learned Laplace transforms. So we'll be focusing on Laplace transform and then maybe inverse Laplace transform as well. Then the applications of Laplace transform, that is the final and initial value theorems. They're very important from control perspective. Final and initial value theorems. And towards the end, we will also be seeing problems on transfer function and impulse response. So basically, we'll be solving problems on Laplace transform, inverse Laplace transform. We'll also see its region of convergence, then the applications of uh, Laplace transform, that is final and initial value theorems. Then we will also see transfer functions and impulse response, and we'll also see one more application of Laplace transform, that is how we can solve differential equations using Laplace transforms. Correct. So let's start. So I'll just recap whatever you have read so that it will be easier for you to understand problems. Quick recap, right? So if we are given a signal xt, right? So if we are given a signal xt, and if we have to find the Laplace transform of this signal, we denote it like this. So this is the Laplace transform of xt. And how do we find it? There's a formula. So Laplace transform of xt is equal to 0 to infinity and e raised to the power st dt, and this is called the Laplace transform. So I hope things are clear to you because you have already gone through the lectures and the slides. So you will be knowing what is S, what's S domain, and yeah. So what are the things? What are these things? I hope everything is clear. If not, so you should better watch those lectures first and then come into this problem solving session. Anyway, I'll try to make sure. So the main purpose of these sessions is that you should be able to solve your weekly assignments. So after 2 hours maybe, so you should be able to solve your assignment, those 10 questions which are being given to you. By seeing this lecture, by watching or by attending this lecture, you should be able to solve those 10 questions at ease. So yeah, this is the formula for Laplace transform. There is something called unilateral Laplace, something called bilateral Laplace, but in any case, we are assuming the systems, the signals to be causal and start only at t equals to be 0. So doesn't make much sense. But yeah, sometimes you'll see this limit starting from minus infinity to infinity, but it will be very well clarified whether you need to take this minus infinity to plus infinity or 0 to infinity. Eventually, in real time, all signals are causal, so they will start from 0. So that's why we use this unilateral Laplace transform, that is 0 to infinity. Correct. So let's do an example. Let's do an example. Let's assume it's a very simple example and it will give you an idea. You must have solved it, but just for recap purpose. So if you have a signal xt is equal to e raised to the power at, and you have to find the Laplace transform. So how you will find it? You will find the Laplace transform that is denoted by xs, because that's an S domain. So Laplace transform of this function will be 0 to infinity e raised to the power minus et into e raised to the power minus st dt. Correct? Which can be solved as 0 to infinity e raised to the power minus s plus a into t dt, or which can be solved. It's a very simple integration. You all know that integration of e raised to the power x. So that will be e raised to the power minus s plus a into t divided by minus s plus a, the limits 0 to infinity. So if you put the limits, it will be, the first term will be 0, because when you put infinity, it will tend to 0, and the second term, it will be 1. So finally, what you will get is 1 divided by s plus a. Correct? So the Laplace transform of e raised to the power at, it's a very, very simple like application. So you need to find, it's actually very important. So you need to remember this. Wherever it is e raised to the power minus at, you should remember it will be 1 divided by s plus a. If it is e raised to the power, if it is e raised to the power at, then it will be 1 divided by s minus a. So you should remember this thing. But there is one more important thing. Let's assume, or like how we got this s plus a, it's very important. You have assumed this thing, this s plus a, you have assumed that to be positive. You have assumed s plus a to be positive. Why? Because this s plus a, if it is positive, then this whole addition, it will be negative. Then and only you will get 0 on putting infinity. Right? If this s plus a is negative, then minus into minus is plus, and then on putting infinity, it will blow up. Right? So you have to make sure this thing, that whatever value you put, the value of Laplace transform, that has to be converging. Like there has to be some finite value, right? So there has to be some finite value of this integral. So that is what is called as the region of convergence. So for example, here, if s plus a is 0, it means s should be greater than minus a. So for s greater than minus a, this integral, it has a finite value. That means it is only finite, or it's only converging in the region s greater than minus a. And this is called region of convergence. What is it called? ROC. You have learned it. I'm just recalling. So what is this ROC? It is the region in S plane. It's the region in S plane in which the Laplace transform exists for a function xt. So the region in S-plane in which the Laplace transform exists for the function is called the region of convergence. For example, in this example, we have s is greater than minus a. So this will be something like this. So we know our S-plane is sigma plus j omega, and s minus a is somewhere here, right? So this is s minus a. So it will be like this. So this region is the ROC for this signal. Correct. So ROC is the region in which your Laplace transform converges, or because this is an integral, you can say this is an integral. So this integral has a finite value. If it has a finite value, then that is the region of convergence. And in that region only, we can say the Laplace transform exists. Correct? So we will see this in the future examples as well. So now consider, let's try to solve this question. Find the Laplace transform of a function ft is equal to 5 plus 4 e raised to the power minus 2t. Right? Anyone? So start solving this with me. Very easy. Again, applying this formula. So the Laplace transform will be f of s is equal to, you know, you have studied these in the lectures that Laplace transform satisfies some properties or has some properties like linear property, time shifting property, convolution, or there are many properties that will go, which are very, very important. So there is one property that is linearity. So if we have to take the transform of this Laplace transform of this function f, we can take Laplace transform on the, yeah, somebody has some question. Please unmute yourself and ask. Anshika. Yeah, please unmute yourself and ask. Okay, maybe you have raised your hand by mistake. So let's try to solve this question. So again, applying the formula, it's 0 to infinity, 5 plus 4 e raised to the power minus 2t into e raised to the power minus st dt. Correct? So my voice is echoing. Wait. Is it fine now? Is it fine now? Can anybody confirm? It's still echoing.
Yes, 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 it is fine, sir.
Okay, thank you. So let's continue solving this question. So we can take it like, we can solve it like this, 0 to infinity, 5 e raised to the power minus st plus 0 to infinity, 4 e raised to the power minus 2t e raised to the power minus st dt. Correct? So from here, I'm just following this. So it will be e raised to the power st and 0 to infinity, 4 will come outside, e raised to the power minus s plus 2t dt, right? So when you solve this, you will get 5 over s plus 4 over s plus 2. Then again, you can simplify it a bit. That is 5 into s plus 2 plus 4s divided by s into s plus 2. This is the Laplace transform of this signal ft, where ft is 5 plus 4 e raised to the power minus 2t. But if you see, it's very boring to solve this problem in such a manner, because it's if we have a complicated function, then it will be very difficult for us to solve this numerical all the time. So there has to be some shortcut method. Actually, in practice, we never use this formula for solving Laplace transforms. So we basically know the Laplace transforms for some functions, and using those values, we can find the Laplace transform of any other function, right? So for that, we will recall some basic transforms of some basic functions, so that we will be able to solve other questions easily, right? So for example, if you have a function x of t is equal to t, then its Laplace transform, so its Laplace transform is 1 by s square. And you all know the Laplace transform of unit step. If we have a one or unit step, its transform is 1 by s. Similarly, you can generalize it if we have e raised to the power n, and you can find its Laplace transform as n factorial divided by s n plus 1. So this is the Laplace transform of t raised to the power n. Similarly, you have, for example, sine of 80. The Laplace transform of sine of 80 is a divided by a square, a square plus s square. Similarly, you have cos of 80. The Laplace transform of this is s divided by a square plus s square. Correct? So now there is this very important property, very important, which you will use. I'm actually saying, see, you will again learn this Laplace transform in your signals and systems course, but we will, in this course, we will uh, see that part, at least we'll touch that part of Laplace transform, which is which will be very, very helpful for us to solve the problems in control systems. So there's this property, this d by dt of xt. So if we have to find the Laplace transform of this d by dt of xt, it will be s times the Laplace transform of that function xs minus the initial value of that function. So this is very, very important. We will see some problems on this as well, and you have some problems in the assignment as well on this property. So if we have differentiation of x, then taking Laplace transform, we get s into xs minus x naught. Similarly, if you have d2 by dt2 xt, the Laplace transform of this is s square xs minus, wait, minus s into x0 minus x dash of 0. So these two properties, they are very, very important. These are very, very important properties as far as control systems are concerned. You will see, you will use these properties while solving differential equations, while finding transfer functions, or in general solving questions in control systems. So they're very important. For example, we will see a question here. For example, if we have a function e raised to the power minus 2at, we already know what its Laplace transform will be, but still we'll try to find it using this formula, right? So if we have to find, so this is, if we have to find the double derivative of this function, so we already know its Laplace transform is what? 1 divided by s plus 2. Right. So what will be, as per this formula, if we have to find, sorry, if we have to find the double derivative of this function, then it will be s square xs minus s into x naught minus x dash of 0, right? So you know what is s square, and all you know what is xs. That is 1 divided by s plus 2 minus s into x naught minus x dash at 0. Now you need to find the value of this function at x0 and then differentiate, and again find the value at x0 at 0, right? So we'll find the value. The value of the function when we put t equal to 0 is it's 1, right? So then when we differentiate it, what we'll get? So if we differentiate it, we'll get e raised to the power minus 2at into minus 2. So when we put the value to be 0, t to be 0, so it will be minus 2. Then putting this value above, it will be x square 1 divided by s plus 2 minus s into 1 plus 2. So this will be the required answer using this property. Using this property, we have solved this. So when you will find the inverse Laplace transform, there you will use this property as well, right? So similarly, if you have integration, if you have integral 0 to t x tau d tau, then the Laplace transform will be 1 by s into xs. Okay, so these things will be more clear when we solve problems. When we'll solve problems in next 10 minutes, right? Now, very, very important as far as control systems are concerned is the initial value theorem and the final value theorem, right? So let's start with, we will solve many problems based on these two theorems. But first, I will just recap initial value theorem. So what does this initial value theorem say? So this helps us to find the initial value of a function in Laplace using Laplace transform, right? For example, if we have a function ft and we need to find xt and we need to find the initial value x naught using Laplace transform, then how we can do that? So then this initial value theorem comes into rescue. So this x naught in Laplace transform, how we will find it? We'll say limiting s tends to infinity s into xs. This will be clear when we solve problems. So this initial value theorem, it helps us to find the initial value of a function using Laplace transform, and it's found using this formula x naught, or a x initial value of x is limiting s tends to infinity s into xs, where xs is the Laplace transform of the function xs xt, right? So if you are given a function xt and if you are given a Laplace transform of a function xt and you're asked to find the initial value of this function, then you can use the initial value theorem. But this theorem, it's valid only it's valid only if the function that we are having is proper. If we have proper function. What does proper function mean? Proper functions are those functions whose order of numerator is less than order of denominator, right? So this initial value theorem is only valid if we have proper functions, and proper functions are those functions which have the order of numerator less than the order of denominator, right? So, but what if we have this improper function. What if we have numerator, the order of numerator is greater than the order of denominator? That doesn't mean that we cannot find the initial value. We can still find the initial value, but in that case, we'll have to take the inverse Laplace and go back to time domain, get the function in time, and then put t equal to 0, and we'll find the initial value. Now, similarly, we have final value theorem. So what does this final value theorem say? It says that if we are given a Laplace transform, then how we can find the final value of the function from that Laplace transform, correct? So here it is x infinity is equal to limit s tends to 0 sxs. Now this final value theorem is valid only, again, if we have a proper function. But again, this is condition 1, and condition 2 is that all the poles must lie in the left half plane, right? So what does that mean? That means we have a bounded signal. So for the next condition is all poles must lie in left half plane, right? With, there is one freedom, with at most one pole at the origin. So in order for us to apply this final value theorem, the condition is that it should be a proper function, that is the degree of numerator should be less than the degree of denominator. The second condition is all poles must lie in the left half plane, or if we have one pole at the origin, that will also be fine. So either all poles should be in the left half plane or at most one pole. If we have two poles at the origin or on the imaginary axis, then we cannot apply this final value theorem. But again, that doesn't mean that we cannot find the final value. We can still find the final value. I'll tell you. I'll tell you that. But in that case, the function will be unbounded and it will be going to infinity. So let's take questions now. So let's assume we have the Laplace transform of a function given as 4 divided by s square minus s, correct? And we are asked to find its final value. So first we'll check whether we can apply final value theorem or not here. So we can check the degree of numerator is less than the degree of denominator. So it's a proper function. Second thing, we'll be checking for the poles. So we have s square minus s equal to 0. It will be s into s minus 1 equal to 0. The poles are s equal to 0 and s equal to plus 1. So what does it mean? It means that we have one pole in the right half plane. So we cannot apply the final value theorem here, right? But again, that doesn't mean we cannot find the final value. So these type of functions, when you will study in the next couple of that, when you have a pole in the right half plane, the response will flow up to infinity. So the system will be unstable. So this system, it's an unstable system. You will learn this in the future classes. Why this is unstable system? Because as t tends to infinity, my response as t tends to infinity, yeah, my response also tends to infinity. It just blows up. So, but let's see. So in this case, we said that, okay, we cannot apply the final value theorem, but how we can find the final value? That's also a question. Now, here, so see, we had this xs is equal to 4 divided by s into s minus 1. Okay, so we need to find the, so in order for us to find the value at like the final value, that means t should be tending to infinity, but we do not have any t here. So we need to go back from this s domain to the time domain so that we get the function in time domain. Then in that time domain function, we'll put t equals to infinity and we will get the response. We will get, then we can get the final value, right? But this is the Laplace transform. This is the function in S domain. In order for us to get the function in time domain, we need to take inverse Laplace, right? So I'll show you how we can take inverse Laplace. Again, using those basic Laplace transforms, we can solve for any function, correct? So, but here, right, see, 4 divided by s into s minus 1. So we need to solve it first using partial fractions method. I know that you must have forgotten that, so I'll just give a quick revision of how we solve this function. We simplify this function first using the partial fraction method because we'll keep on using this fraction method in our next problems. So we can write it like this: a by s plus a2 by s minus 1. Then we can simplify it. So it will be 4 is equal to a into s minus 1 plus, sorry, a1. And here it will be a2 into s. What I did, I multiplied, yeah, I took the LCM, or I multiplied both sides by this s into s minus 1 term. So this will vanish up. This will vanish up here. And here the term will be s minus 1, and here the term will be s. Again, simplifying it a bit. So it will be a1s minus a1 plus a2 into s. 4 is equal to s terms we will collect. a1 plus a2 is s minus a1. Now what we have to do, we have to compare. There are many methods. This is one of the method. I'll explain in other questions how we can do this partial fraction method using other methods. So now this is the s term and this is the constant term. Here we can write it 0s plus 4. So if we compare the coefficients, we'll get a1 plus a2 is equal to 0 and a1 is equal to minus 4. So when a1 is minus 4, then a2 is plus 4. Or we can write the function as a1 is minus 4 by s plus s minus 1. Right, so now it's very easy for us to take the inverse Laplace. So what is the inverse Laplace of this? Minus 4, we know this is ut. And also we know here it is e raised to the power t, right? So it's 4 ut plus, it's minus 4 ut plus 4 et ut. So I use this, the Laplace transform of minus at. It is 1 divided by s plus a. Similarly, if it is plus here, then it will be minus here. I use this property. So, so yeah. So we got the value, we got the Laplace transform. So this is xt. Now, if we have to find the final value, that will be x infinity. So if you put infinity here, this will, as t tends to infinity, it will go to infinity, and similarly, this will also go to infinity. So it will be infinity. So that's why I earlier said that it's unbounded signal, unbounded system, right? So why we cannot apply the final value theorem here? Because the value will come out to be infinity. That's why we can also, the system is unbounded. Now this will be more clear in the subsequent problems. Now do another question, that is x of s is equal to 2 into s plus 1 divided by s into s square plus 4. So find initial value and final value using IVT and FVT. So you have to use initial value theorem and final value theorem to find the initial values and the final values of this function. So first we check whether we can apply our final value theorem and initial value theorem. So for that, the transfer function needs to be proper. So the function needs to be proper. See, the numerator degree order is 1, and in denominator the order is 3. 1 is less than 3. It's proper. Again, now we need to check. We need to check the poles. So s into s square plus 4 is equal to 0. It means we have 3 poles, one at s0 and other one s is equal to plus minus j2. Correct? Correct. So what did we say? This is for final value theorem. For final value theorem, we said that all poles have to be in the left half plane. They have to lie in the left half plane, or at most one pole can be at the origin. So if we plot this, s equal to 0 is here, and then we have one pole here and one pole here, right? So we have more than one pole. We have more than one pole at the origin, so we cannot apply the final value theorem. But yeah, there is no condition. There is no such condition for initial value. So we should be able to find the initial value. So how we can find the initial value? X of 0 is equal to limiting s tends to infinity s into xs, which is equal to limiting s tends to infinity s into ss is 2s plus 1 divided by s into s square plus 4. Correct? So this s and this s will get cancelled, or no, let's not cancel it because that will make the system complicated. We can just solve it a bit. Limiting s tends to infinity, we will have 2s square plus s, and here it will be s cube plus 4s, right? So if you now uh, you have to put infinity here. So if you put infinity, so it will be infinity over infinity. So it's the improper way. So what we have to do, we cannot solve it like that, right? We have to take things common. So we will make it simple here. We'll take s square. Yeah, s will take common. So s here it will be 2s plus, or we can take s square as common, right? We'll take s square as common. Then what we will get? We'll get 2 plus 1 over s. Then here s square, we will get s plus 4 over s, right? This s square and s square will get cancelled. When you put on infinity here, this will be 0. Similarly, when you will put on infinity here, it will be 0. But again, we have another s. So you will put it infinity. So it will be a huge number. So 2 divided by a huge number, that will also be 0. This will be 0, right? So I hope this is clear. So I'll just simplify it. For example, you are putting s tends to infinity. So we have 2 divided by s here, limiting s tends to infinity. So if you put s equal to 10, then you will get some value. Then if you put s equal to 100, some value. And if you put s 1000, that value will go on decreasing. And finally, as s tends to infinity, that value will tend to 0. But why I did like this, why I solved it like this by taking s square common, because this is an easier way, and you will see in the subsequent problems that by doing this, we save a lot of time. Next question, find the initial value and the final value of the function 7s plus 6 divided by s into 3s plus 5. Okay, so again, we can see the degree order of numerator is less than that of denominators. This is 1, this is 2. So we can apply initial value theorem. Similarly, now we have to see the poles. The poles also are in the left half plane. So we can also apply the final value theorem. Can you now try finding x naught and x infinity? Can you try? Can you try and tell me the values? Take 2 minutes and solve it. Anyone? What are the initial values and final values? Again, you have to use the initial value and the final value theorem. It's very easy. Okay, let me solve this
7
for
by
you.
3.
Yes, initial value should be 7 by 3 and final value.
Let me calculate.
Yeah, yeah, sure. So initial value he has calculated as 7 by 3 and final value
6 by 5.
great. So final value is 6 by 5. For others, let me just solve it, because there's the same thing which I said in the earlier problem. We have to take care of infinity over infinity issues or 0 over 0 issues. Right. So let's solve this. For example, let's find the initial value. What will be initial value? It will be limiting s tends to infinity, s into xs. And what's xs? Xs is 7s plus 6 divided by s into 3s plus 5. Correct? So this s and this s will go. We'll get limiting s tends to infinity 7s plus 6 divided by 3s plus 6. Now, if you put infinity, it will be infinity over infinity, and which is not required, which is not desired actually. Now, what you will do, you will solve it or manipulate it. You'll solve it like this. Limiting s tends to infinity. We'll take s common. So if we take s common, what it will be 7 plus 6 over s divided by 3 plus 6 over s. Sorry, it's 5 here. 5 over s. Now we can put the limit. So when you put tends to infinity, s tends to infinity, this will blow up to 0. This will again go up to 0. Then what we will get is, we will get, and again this and this s will go, and we will get the value as 7 over 3, right? But you need not do this in the final value calculations, because in the final values, what you have to do, for example, x infinity is limiting s tends to 0, x into xs, which is equal to limiting s tends to 0, s into 7s plus 6 divided by s into 3s plus 5. Correct? So this s and this s will go. When you put 0, this will 7s and 3s will also go, and you will get 6 over 5 easily. So now, if you have understood, can you please solve this question? Find the initial value and final value using the initial value and final value theorem if xs is s plus 1 divided by s plus 2 whole square plus 10. And your options are 14, 1 by 14, b 1 comma 0, c 0 comma infinity, d 1 by 14 comma infinity. Now find the initial value and the final value of the function s plus 1 divided by s plus 2 whole square plus 10.
Option B.
Okay, option B. Correct. Anyone else who has problems like how this option B gave? So in the same way, there are these questions in the practice assignment. So if xs is s plus 1 divided by s into s plus 2, can you find the initial value and final value? Anyone? It's very simple. If anybody has any doubt or he or she has not understood it properly, we can do some more problems. The main outcome of these sessions is that you should be able to solve your weekly assignments. And there are few questions on initial and the final value theorems.
Initial value is 1
Okay, correct. Only one person is answering.
and final value is half.
Great. So things are clear now. Uh, if anybody has any doubt, then we can solve some more problems. Otherwise, we can just move on other topics. Anybody, if anyone has any doubt, otherwise we can just move. Okay, there is this very important, very interesting question. Let's do this. Question. Given that f of t, or the Laplace transform of ft, is equal to 3s plus 1 divided by s cube plus 4s square plus k minus 3 into s. Right? So the Laplace transform of a function ft is this. If limiting t tends to infinity, f of t is 1, then find the value of k. This is a very interesting question. So if you have understood the concept of initial value and the final value theorem, then you should be able to solve it in just a minute. You should be able to identify what is given and what is given, and then accordingly you should be able to proceed.
F of t is given.
Yes, so what is given? Okay,
Left
anyone
hand
has
side is
find. So you are given this. You are given the final value of the function. So the final value of the function is given. So is it final value? So if it is final, yes. So this is the final value that is given, then how we will proceed? So final value, that is f infinity, it is given. You already know from final value theorem that final value is given by this, and it's given to be 1. Correct? So now we'll put on values. So limiting s tends to 0, s, what is xs? Xs is 3s plus 1 divided by s cube plus 4s square plus k minus 3 into s. Correct? So we can take common here. Limiting s tends to 0 will be s 3s plus 1, or if we take s common, it will be s square plus 4s plus k minus 3. this s and this s will go, and when we put the limit, this will go, this will go, this will again go. It will be 1 minus k minus 3 is equal to 1, implies k minus 3 is 1, implies k is 4. So have you understood?
Yes, sir.
So anybody has any doubt? So then otherwise we can just move forward. I hope now you should be able, or you would be able to solve all the questions on initial value and final value that are given in the assignment. Still, before we end, can you solve this question using, can you find the final value? Can you find the final value of the function 1 over s into s minus 1? Can you find the final value of this function? This is the last question, then we'll move forward. But using final value theorem.
-1.
Can you cross check? Anyone else? Only Vijay Pawar is answering. So anyone else, please participate. It should be interactive. Again, if you see, I said for the final value theorem to be valid, the function has to be proper and unbounded. That is, all poles have to lie on the left half plane with at most, like, if not all, like if there is any pole that is in the right half plane, we cannot apply. So here clearly we can see the function is proper, but we have two poles. One is at s is 0 and other is s is 1. So this pole, it lies in the right half plane. So this system is unbounded. So it will blow up to infinity. So we cannot apply final value theorem here. So you have to be very careful, right? So because if you apply the final value theorem without seeing this condition, then what will happen? This s and that s will get cancelled, and you will get answer as -1. But that will be wrong. So you have to be very careful. Your assignments will have such questions where you will have to be very careful in checking whether we can actually apply the initial value theorem or not. So is this clear?
Yes, sir.
Great. So okay, let's move forward and do a question on inverse Laplace. So how to find the inverse Laplace? If xs is given as s plus 5 divided by s plus 1 and s plus 3, so how we can find xt? So how we can find xt, that we'll see in this question. So in order for us to find the actual function in time domain from the Laplace transform, like we will make use of the partial fractions as I did earlier in a question. So here I will also make use of partial fraction that will make our calculations easier. So we have s plus 5 divided by s plus 1 into s plus 3. We can write it like this: a1 over s plus 1 plus a2 over s plus 3. So you all of you must be knowing the partial fractions method. So simplifying it, taking LCM, so we will get s plus 5 is equal to a into s plus 3 plus, sorry, a1, this is a2 into s plus 1. Correct. So one way to solve this is, okay, I'll follow the same method which I followed earlier. So it will be s plus 5 a1 into s plus 3a1 plus a2 into s plus a2. We can rewrite it as a1 plus a2 into s plus 3a1 plus a2. Now comparing coefficients, we can write a1 plus a2 is equal to 1 and 3a1 plus a2 is equal to 5. Correct? So from here, we can find the value of a1 as 1 minus a2 and put it here. So it will be 3 minus
Answer is 2
3a2.
minus 1.
Okay, okay, good. So let's straight away write here. The answer is we will get a as 2 and b as minus 1. So anybody has any doubt on this, how we get the answer, or is everybody comfortable in solving partial fractions? Then this can save our time. Then how we can write the function? We can write it s plus 5 is s plus 1 into s plus 3. Can directly write it as 2 divided by s plus 1 minus 1 divided by s plus 3. Right, and now we know the Laplace transform of e raised to the power minus at is equal to 1 divided by s plus a. So we can make use of this, and what we will get? What we will get? It's very easy. So inverse Laplace is very easy. What you have to do is to find the partial fraction. So what you can do is you can find that you get the answer as e raised to the power ut minus e raised to the power minus 3t ut. That's the inverse Laplace transform for the above function. So the main thing in finding the inverse Laplace transform, it is that you should be able to solve the partial fractions. So we will come back to this inverse Laplace transform later. We will do some other questions first. Then if we can solve some more questions on inverse Laplace, because this is not difficult. Oh, okay. So there is this question. The question is, we are given d2y over dt2 minus 5 dy by dt plus 6y is equal to 0, with y at 0 is equal to 2 and y dash at 0 is equal to 2. Then find the value of yt at t is equal to 1. So this is actually a very important question, and this will clear many of your concepts. This question. So in this question, we will have inverse Laplace. So when we have inverse Laplace, we have partial fractions. We also have the properties of Laplace transform that we apply here. So you should know that I explained that property that d2y over dt2. So what should be the value of this? If we take Laplace transform of this, so if we take Laplace transform of this, I should get s square ys minus s into x at 0 minus x dash, right? Similarly, dy over dt, after taking Laplace transform,
Whether
it
it
will
is
be,
x of 0 or y of 0.
sorry. Yeah, it's y of 0. Sy of 0 minus y dash at 0. Similarly, we have y at 0, right? So after we put these values in this equation, so what we will get? We will get s squared ys minus s into y naught minus y dash at 0 minus 5 into s into ys minus y0 plus 6ys is equal to 0. On simplifying and putting on in the values, what we get, s square minus 5s plus 6 ys minus 2s minus 2 plus 10 equal to 0, or we can get y of s as 2s minus 8 divided by s square minus 5s plus 6. You can write it like this, s minus 3 into s minus 2. So anybody has any doubt? Like until this? Now what we have to do, we will find the inverse Laplace. So when we find the inverse Laplace, we will get yt. Then when we find yt, then we will put t equal to 1 and we will get the value at y1, which is actually desired, right? So now the task is to find the inverse Laplace. So for inverse Laplace, we'll first find the partial fractions, correct? So solving using partial fraction. So 2s minus 8 s minus 3 into s minus 2, it will be a1 s minus 3 plus a2 s minus 2. So on solving, we find the value of a1 is equal to 4 and a2, sorry, we get the value of a2 is equal to 4 and a1 equal to minus 2. Therefore, we get this 2s minus 8 s minus 3 into s minus 2 is equal to minus 2 s minus 3 plus 4 over s minus 2. Then finally, if we take the Laplace transform, we will get minus 2 e raised to the power 3t ut plus 4 e raised to the power, it will be plus 2t, right, ut. So this is our inverse Laplace. Then when you put the values y1, that is, you put t equals to 1, you will get the value as 10.615. right? Is this clear? So this question, this had many parts. First, we knew the properties of uh, the, the Laplace transform. From the properties, we wrote the Laplace of differentiations, second derivative, and the first derivative. And then we solved it, found the inverse Laplace. For inverse Laplace, we took the partial fractions. Then finally, we put t equal to 1 and we got the values, right? So should we move forward? Yes. So there are many properties of this Laplace transform. Uh, I will not cover each one of them, but you should try to solve problems on your own on other properties, because in your assignment, you have only 10 questions. So for 10 questions, you need only 2, 3 properties, right? So there is this very interesting property of convolution. So we'll quickly say this convolution. So convolution you have studied in your lectures. It's actually a mathematical way of combining two signals to get another, right? So we basically, it's an integral, right? So it actually measures the overlap of one signal over the other as it is shifted over, like it measures the overlap of one signal as the other signal is shifted over that, right? But I'm not going into that. I'm just interested in the property of this convolution, like when we take Laplace transform. So for example, if we have a function xt, then it has a Laplace transform of xs. We have another function yt. It has a Laplace transform of ys. This has an ROC R1. This has an ROC R2. Then the convolution of xt and yt, if we take the Laplace transform of this, it will just be the multiplication. And the ROC will be R1 intersection R2, right? So if I have convolution in the time domain that corresponds to multiplication in the S domain. Okay, so this is a very important property. Now, based on this, we have a question. So, question is, find the convolution of e raised to the power minus t with sine of t, right? So if we have to find the convolution of e raised to the power minus t with sine of t, so there is this thing, you can apply convolution stuff and solve it. But if we make use of Laplace transform, then this will be very easy. See, we know the Laplace transform of this e raised to the power minus t, it is 1 over s plus 1. Similarly, we know the Laplace transform of sine t is 1 over s squared plus 1. Now, convolution in time domain is equivalent to multiplication in the frequency domain. So the Laplace transform of this convolution of these two signals, what will it be? It will just be the multiplication. Correct? So what you will get? Now you get 1 over s plus 1 over s squared plus 1 Now this you got, but again, you have to find convolution, and convolution is in time domain. So what you will do to find the time domain signal? So again, you will take inverse Laplace. For inverse Laplace, you will take partial fractions. So the partial fraction of s plus 1, s squared plus 1. Now you have to be very careful here. It will be a1 over s plus 1 plus a2s plus a3 over s squared 1, because in the numerator we have, in the denominator we have a quadratic function, then in the numerator we will be having a linear function. So I hope these things are very clear to everyone. So on solving we get a1 is equal to a2 is equal to a3 is equal to 1/2. Then we know that this will be 1/2 1 by s plus 1, 1 by s squared plus 1 minus s squared plus 1. So right, so on solving, then you'll get the convolution finally as this. Yeah, it will be e raised to the power minus t plus sine t minus cos of t.
So the minus sign minus s by s square plus 1. This should be
Yeah,
plus, no?
yeah, probably this
Minus.
a2 is minus 1 by 2.
Okay, okay.
Yeah, because we have not solved it. So a3 is this, a1 is 1 over 2. Right, so making use of this Laplace transform convolution stuff also becomes very, very easy, right? So now there is another property. Actually, we have to cover transfer functions as well. So let's be very quick. Yeah, Asad Khan has any problem? Yeah, please. Yeah, A2FC. Whenever you do partial fractions, so if you have uh, like a linear function in the denominator, then you take a constant in the numerator. Then if you have a quadratic function in the denominator, then in the numerator, you take a linear function and so on. So here, if you see, you have a linear function. So then you take a constant. Then if you have quadratic, you take a linear. If you have a cubic, you take a quadratic. So let's assume if you had something like this in the denominator, x cubed plus 2s squared plus 3s plus 1 or whatever. So in that case, what you will do, you will take as squared plus a2s plus a3. Then you will solve it. It will be very complicated that way to solve. But yeah, the key idea is whatever you have in the denominator, you have to take one function, one order less than that in the numerator. Right, so now there is another very important property that is called as time reversal. So for example, if you have a function xt, Laplace transform is xs, then if you have x of minus t, then the Laplace transform will be x of minus s. For example, if you have e raised to the power at ut, you know the Laplace transform is 1 over s over a with s greater than minus a. I already told you this, but now if we do the time reversal, that is, it becomes at and u minus t, then it will be minus s plus a, and I will say also minus s minus a, which will be minus, it will be minus minus, this will be s less than a. Right, so this is time reversal property. You need to change the sign of s both in ROC as well as wherever this s appears. Now, based on this, you have one question in the assignment where you have to find the Laplace transform and its ROC for a combination of two signals. For example, when you have two signals in the addition, right? So, for example, the question is xt is equal to 3e raised to the power minus t ut plus 2e raised to the power t u minus t, right? So again, so if these two signals, they are in addition, so we'll take first the Laplace transform of both these functions, then the ROC will be the intersection of the individual ROCs. For example, if this is ROC1, this is ROC2, so the ROC of the signal is R1 intersection R2, right? So so this is how we find the ROC of signals in addition, right? Now let's solve this. So we have first 3e raised to the power minus t ut. We know its Laplace transform is 3 divided by s plus 1 with ROC s greater than minus 1. Then we have this thing. We have 2, what we have? 2e raised to the power minus t u minus t, right? So we'll first do the a different version. Sorry, it's plus t probably. Yeah, it's plus t. So what we will do first, we will find the Laplace transform of this signal. We know the Laplace transform of this signal is 1 divided by s plus 1, right? So with ROC, s is greater than minus 1. But now I'll do the time reversal. So it will be plus and this will be minus. Then it will be 2 divided by minus s plus 1. Minus s is greater than minus 1. S is less than 1. Correct? So now we have found the Laplace transform, but now we have to find the ROC. So the ROC of this signal is greater than minus 1, and the ROC of this is less than 1. So how we can find the ROC of the function? So the one function ROC is greater than minus 1. So ROC is like this. The other function, this is 1, this is minus 1. For the other function, the ROC is here. Now, then what will be the ROC? This region, right? This region is the ROC of the signal, right? This combined region, which is the intersection, this is the ROC of this combined signal. Now, what if there was no intersection? Then we can say a Laplace transform for this signal does not exist, because I said earlier, the Laplace transform, that's an integral and that has to have a finite value, right? So if there is no common region, then we can say that Laplace transform does not exist. Now let's quickly move to transfer function. Correct. So you all know transfer function is actually sometimes denoted by g of s or h of s. It is the Laplace transform of is the Laplace transform of output over input. So it's the ratio of Laplace transform of output to the input, but with all initial conditions assumed to be 0. So for example, if this x is a function, oh, sorry, like this, with initial conditions assumed to be 0. This is very important point because when we solve problems, we will make use of this point. This initial conditions are all 0. For example, let's quickly solve this question first. This is a practice problem in your assignment question. So using the Laplace transform for xt in the following differential equation, the differential equation is x double dot of t plus 5x dot of t plus 3x of t is equal to 10 ut. Then find transfer function x of s over u of s. Again, when it's transfer functions, initial conditions are 0. 0 initial conditions. Correct? So how can we solve this? I already told you we can make use of Laplace transform, but now you already knew this. For example, if we have d2x over dt2, it was s square xs minus s into x0 minus x dash at 0. So this is the property of Laplace transform. But now we assume the initial values to be 0. This will vanish, we'll only get this. So using this, we can easily write the above equation as, we can easily write it as s square xs plus 5s xs plus 3xs is equal to n u of s. Correct? So we can solve it a bit. We have to find xs over us, which is equal to n over s square plus 5s plus 3. So this is the required transfer function. So this transfer function makes our stuff very easy because now we do not need these initial conditions. So our process is it becomes simpler when we use this transfer function stuff, right? In the last week, we derived governing equations of a spring mass damper. For example, we had the equation F as m d2x over dt2 plus b dx over dt plus kx, right? So now if you are asked to find the transfer function of this system by taking displacement as the output and the force as the input, you can easily write this as 1 over s square plus b into s plus k, right? Because it has the similar form as we have the above. So any mechanical system, so you can now easily find the transfer function of any mechanical system using this Laplace transform. For example, we had another
So
question.
here m will be there, na? M s square.
Yeah. So let's do this question. This will just revise your last week stuff. This is K2. This is K1. Here F is acting. Displacement is X. And here we have the friction that is actually coming from the damping, or we can write it as the damper, which is F. Right? So for this, we have already solved this in the previous lecture. For example, using the nodal method where I assume a node here, X, then drive this mass M and the ground here. Then I saw this force is being applied to this mass. So this is force. It's being applied to this mass. Then we have one spring, another spring, and we have a damper. Right? So we have solved it. And the equation that we got was F is equal to M d2x over dt2 plus F dx over dt plus k1 plus k2 over x. Now, if we have to find the transfer function of this system, xs over fs, what will it be? Very simple. Again, the same thing. ms square plus fs plus k1 plus k2 into, k1 plus k2. So are things clear? Now, if you have understood this, you find the transfer function of this circuit. So we have this current I flowing through this circuit. V is the voltage, right? So if you have understood, now find the transfer function of the circuit. Okay, again, take current as output and voltage as input here. So it will be specified to you what you have to take input and what you have to take output. Right? We can write Kirchhoff's laws, very simple. V of t is equal to Ri of t plus L di by dt. Now taking Laplace, we have Vs is equal to Ris plus L. And di by dt, we know this is what? S into Is. Since this is the transfer function, we assume all initial conditions to be zero. So there is no initial condition here. All they have assumed to be zero. Now, if we have to find Is over Vs, it will be 1 plus SL. Right? This is the transfer function. So you have to be very careful while you apply the Laplace transform, because as I said earlier, this differentiation property, this will keep on coming. So some very important properties of this transfer function is that it's valid only for LTI systems, right? So this transfer function, it's valid only for LTI systems. We have learned in the previous class what are linear, what are time invariant systems. So similarly, again, we are assuming the initial conditions to be zero. And one more thing is that this transfer function, this is independent of the input, right? So this is a very important point. For example, if you have a mobile phone, so the outcome, it doesn't like the outcome of the mobile phone, it has nothing to do with input. So the transfer function has nothing to do with input. So we have a mobile phone, it has a transfer function. Then the output will be dependent on input and the transfer function, but the transfer function has nothing to do with input. I will give one input, the mobile will has the same thing, I'll only get different output. Similarly, other people will also give some input. The person will get the other output, but yeah, the transfer function remains the same. So it is independent the input. You have to remember this. Now there is this question in your assignment. Yeah, let's solve this. Similar question is in your assignment. The transfer function of a system is given by g of s is equal to 1 over s square plus as plus b, where a is not equal to 0 and b is not equal to 0. Then if one of the poles, if one of the poles of the system is -5 plus 7i, then find a and b. You have a similar question in your assignment. So if you are given a transfer function and you are given this thing that one pole is -5 plus 7i, then you are given a and b. So then you have to find the value of a and b. You have options. I'll give you options. Option A is 37,5. Option B is 37,49. Option C is 74,10. Option B is 10,74. Again, you'll have to check. Anyone, should I solve it or you're in process of solving it?
D answer.
10 over 7, 10,74. Yeah, that's the correct answer. So let's quickly solve it for others. So we know that we are given a pole that is -5 plus 7i, and it's a complex pole. And total, we have two poles because s is square. So when this is complex pole, we know that complex poles occur in pairs. So another pole is also complex, and that is -5 minus 7i. Correct. So if S1 is -5 plus 7i, then S2 will be -5 minus 7i, because we know that complex poles occur in pairs. Complex poles occur in pairs. Now what we can write, we can just reformulate the transfer functions that we are given. We can just rewrite it as S plus 5 minus 7i, because we are writing it in the denominator, S plus 5 plus 7i. And what you will do, you will just multiply this equation and you will get 1 over s square plus 10s plus 74. So clearly we can see this is A and this is B. This was a very simple question, and indeed it is a very simple question. The only thing you have to do is you have to use your concept, that is this complex poles occur in pairs, and then you can solve this. Now let's do two more questions and then we are done, but they are very, very important questions. They check all your concepts, whatever we have learned in this lecture so far, so they check all. So please write this question with me. So a system is described by the following differential equation, that is d squared y by dt2 plus 3 dy by dt plus 2y is equal to xt, right? So this, it's given in the question that the system is initially at rest. The system is initially at rest. The question is then, for input x of t is equal to 2ut, the output yt is. I'll give you options. I'll give you options. Option number one is you start solving. Please mute yourself. Somebody has unmuted. Yeah, unmute. Yeah. So 1 minus 2 et plus e raised to the power 2t ut. Option B is 1 minus 2t 2e raised to the power 2t ut. Option C is 0.5 plus e raised to the power minus t plus 1.5 e raised to the power minus t ut, and D part is 0.5 plus 2e raised to the power minus t, 2e raised to the power minus 2t ut. Yeah, these are the options. It's a very simple question, but yet conceptual. Anyone?
Is the A option, sir?
A option. So A option is yes. A option is correct. So what about others? So can I know Vijay Pawar? So can I know, like, are you currently in BTech final year or like what?
No, no, I am an associate professor.
Oh, sorry, sir. So where?
I am in Maharashtra, Jalgaon.
Okay. So it's a state government college.
No, it is a yes, private college.
Okay. So you have finished your PhD?
No, I have been appearing for PhD. In the last stage, I am doing.
Okay. But still, like you're still doing this course. It speaks a lot because other people, like some 4,000 people have registered for this course, yet only 6 people have joined.
Yes.
So I actually intentionally kept this session on Sunday so that people can join at ease, because the option was Friday. Normally that's a working day and it's difficult for people to join. I expected a lot of attendance, but yeah. So let's solve it for others. Maybe they're not able to solve it. So there is given this very important point here that if the system is initially at rest, so it means that all initial conditions are zero. We only have to bother about the current values in Laplace transform, neglecting all the other values. So the equation is d2y over dt2 plus 3 dy by dt plus 2y is equal to xt. So if we take the Laplace transform, it will be s squared ys plus 3sys plus 2ys is equal to x of s. Now, since x of t is 2ut, x of s will be 2 by s. We can put the values, and finally what we'll get y of s as 2 divided by s into s plus 1 into s plus 2. Now, since we have to find actually the inverse Laplace of this, then again we will go for partial fractions. So it will be 2 into s plus 1 into s plus 2 is equal to a1 over s plus b. Sorry, yeah, let's keep uniform notation. A2 into s plus 1 plus a3 into s plus 2. We'll find the values of a1 as 1, a2 as minus 2, and a3 as 1. Therefore, our ys will be 1 over s minus 2 over s plus 1 plus 1 over s plus 2. Then taking the inverse Laplace, we'll get 1 minus 2 e raised to the power minus t plus e raised to the power minus 2t ut. So this is the final answer. So let's solve one more final question for the day. That is question. I hope like by solving these much of questions, you should now be able to solve all the questions of the assignment. There are not difficult questions, and I hope I have covered all types of problems. There is one from the transfer function, couple from the transfer function, and one from the like inverse Laplace, Laplace, initial value, final value theorem, and one from, again, the combined ROCs, which you have to find. So now one question, just a good question. Let's do it. Yeah, we have some time, so let's quickly do this question. We are given an LTI system, which has a rational transfer function with simple poles at s is equal to minus 2 and s is equal to minus 4. And one simple 0, s is equal to minus 1. And then a unit step is applied. So a unit step is applied as the input of the system. This is clear. Now, at steady state, the output has constant value 1. you are being asked to find the impulse response. Find the impulse response. This was taught in the lectures, but I have not revised it. So quickly, if I have to revise it, so this transfer function, this was output Laplace transform of output over Laplace transform of to the Laplace transform of input, given all the initial conditions are zero. So now, if you give this RS is the input, so now in time domain, if you give this RT, let's assume this RT, we give as an impulse function. So if we give this impulse function as an input, then what we will get, and this GS is then uh, like it's being denoted by HS for simplicity, this HS will be CS. Or in other words, this HT in time domain, it will be C of t. So when we give input as an impulse function, when we give input as an impulse function, then the response that we get is called as impulse response, right? So now if I have to, this is actually a very well established concept. So in simple words, I'll just tell you this transfer function. One definition was it is the ratio of a Laplace transform of output over input, and another definition is it is the Laplace transform of impulse response. You'll just revise it. So transfer function is the Laplace transform of impulse response. This concept we will use, right? So transfer function, it is the Laplace transform of impulse response. Now you will just recap it. Now coming to the question. Coming to the question, we are given the system has two poles, two simple poles S2 and S4, and one simple zero at -1. So based on this, can we write the transfer function? We can of course write the transfer function based on this information. It will be like this, right? So we can write the transfer function based on zeros. This is a zero. These are poles. But again, we do not know what is the gain, the constant gain that's multiplied with the system. So we can keep it as k, because we do not know that. That can be anything. Based on the information that we are given that the system has two poles and one zero, and both are simple, so you can easily write them. And we are given, one more thing we are given. We are given that at steady state, the output has a constant value 1. So this steady state means H infinity. It means output has a constant value 1. It means using final value theorem, we can find the value of k here. Correct? So we can apply the final value theorem. So the final value theorem says limiting s tends to 0, s of h of s, which is equal to limiting s tends to 0, s into k of s plus 1 divided by s plus 2 into s plus 4. Correct? So okay. I have forgotten one thing here. So this input I have not considered. It's given a unit step input is applied. So when we apply in unit step input r of s to be 1 over s, then here it will be 1 over s here. Similarly, we will have it 1 over s. This s and this s will get cancelled. Then what we will get, and we know the value of this is 1, then we will get put s equal to 0. When s is 0, this will vanish, this will vanish, this will vanish. So we will get k over 8 is equal to 1. We will get k is equal to 8. Now we got h of s. H of s is 8 h of s is 8 into s plus 1 divided by s plus 2 into s plus 4. Correct? Now, what I said, sorry, somebody's, I said, uh, transfer function is the Laplace transform of impulse response. And if we take the inverse Laplace of this transfer function, we should get the impulse response, right? So again, we will take the inverse Laplace, that is 8 into s plus 1 divided by s plus 2 into s plus 4 is equal to a1 s plus 2 plus a2 s plus 4. And on solving, we get is as 8s plus 1 divided by s plus 2 into s plus 4. We get it as 4 divided by s plus 2 plus 12 divided by s plus 4, right? So then when we take the inverse Laplace, which is actually the impulse response, the impulse response will be, right? So I think it's -4, whatever you'll have to check. So it will be -4 e raised to the power minus 2t plus 12 e raised to the power minus 4t ut. So this is the required impulse response. I'll again quickly recap what was given in the question. So the question asked us that we are given a system which has two poles, two simple poles at -2 and -4, and a simple zero at -1. So based on this information, we should be able to write the transfer function, that is CS over RS. We should be able to recollect or reformulate based on these poles and zeros. Then the question is saying a unit step is applied. A unit step is applied, right? It means the input is 1 over S. Then the question is saying at steady state, the output has a constant value. So steady state means once this transients have died out, so we are getting the output as value 1. So it means final value is given, right? Final value, the steady state, it's a time domain property. So final value is given. We already know the final value theorem. So, and then we are asked find the impulse response. So there are many properties mixing up in this question. So that's why this is a very important question, because it needs a concept of final value theorem. It needs the concept like impulse. This transfer function is the Laplace transform of impulse response. It also needs the basic concept that how we build the transfer function from poles and zeros. Right, so then based on this, we can reformulate the transfer function as this, and then we will use the input as 1 over S, find the final value, apply the final value theorem, we will get the value of K as 8. Then again, we will find the inverse Laplace using partial fraction method. We will find the coefficients, and then finally, the inverse Laplace of the transfer function is actually the impulse response of the system. So you will just revise these things. So I hope with this, we will conclude our session, and I hope that now you should be or you will be able to solve all the questions from the assignment, and you should be getting the links for these videos, like for these sessions, recorded sessions, and also the notes, I think. So yeah, anybody has any questions? So otherwise, we'll just conclude.